Hello everybody, my name is Timos Ampelikiotis. I'm working as a software engineer in virtual open systems, and today I want to present to you Virtio-loopback technology and its latest developments. More specifically, we are going to focus on the multi-device and the prioritization feature that we added in the last year development. Let's go through the agenda and the structure of today's presentation. We will start by recapping what Virtio-loopback technology actually is and why it is useful. Then we are going to jump on the latest feature added this year, and we are going to continue with other activities that happen during those developments. At last, we are going to finalize this presentation by exploring new use cases for Virtio-loopback and future development that might be interesting for AGL. So what is Virtio-loopback? Virtio-loopback stands as a hardware abstraction layer between applications and user space driver. By that means that it tries to mimic the behavior that was happening in a virtualized environment, an application running in a virtualized environment, not knowing any details for the underlying hardware, which was handled after all from the hypervisor or user space drivers running in the host system. Now we would like to port all of these things, the Virtio drivers and the user space components, on a native systems without any virtualization happening. What's the benefits of this technology? Existing user space drivers and applications that were used for VMs can be ported in native systems and modified. Data are shared from the host kernel to the user space, and well-tested technologies as Virtio and VSuser are used into this architecture, which guarantees openness and stability. This is a figure that showcases very briefly how Virtio-loopback is able to act as a HAL. More specifically, it defines two new components, one in the kernel space and one on the user space, try to route the whole traffic happening from the Virtio drivers to the user space devices. Let's have a look on those two components. The first one is a kernel component and works as a new Virtio transport layer. Its main responsibility is to take all these read and write commands coming from the Virtio block, can, sound, etc. and route them to the user space. Then it will mainly focus during the data plane, the data exchanges, by sharing this data to the VSuser device. The second important component is called adapter, and it's a user space application which oversees the communication between the other components, manages the configuration and the initialization of the whole architecture. During the data exchange period, it doesn't intervene at all, so it doesn't add any, it doesn't have any more impact. Now let's have a look on the multi-device support and prioritization features added this year. The multi-device feature enables us to run different applications on top of Virtio-loopback and accessing hardware concurrently. This work has already been merged under Gerrit and MetaAGL devel layer, and links will be provided later so you can have a look. A demo which summarizes what we were describing in the previous slide was presented in the OSSJ 2024 event and was demonstrating two applications, one for sound and one CAN message simulator, which they were utilizing the Virtio-loopback architecture in order to access the VSuser drivers and from there the real hardware. Those two applications could be interacted from the AGL Flutter interface, and the user was able to change songs and see differences on the speed of the car and the accelerometer. On top of what we've seen for the multi-device support, the prioritization feature was added as an experimental activity to explore the possibility of manipulating the traffic from those different devices and being able to prioritize one over the other. To do so, we implemented a new scheduling mechanism into the kernel component, which implements group for assigning the Virtio devices and credits for prioritizing those devices if they are part of the same group. This mechanism can be enabled during the startup and configured per device. The code has been already merged under meta-eg virt layer, and those links can guide you to find the patches. In this slide, we want to put in practice the theory that we have described before about this feature, and we showcase 4 different BLK devices, which the first and the second one are assigned to the same group with a different number of credits, but at the same time 3 and 4 devices are running in parallel, unregulated, and not using this feature. The first figure shows the initial configuration as we discussed. The colored figure shows the performance relation between the devices. 3 and 4 are having exactly the same performance, and at the same time 1 and 2 combined are going to be equal to 3 and equal to 4. Now, at the same time, BLK1 and BLK2 are having in relation 1 to 2 performance. On the right side, you can see the results of the FIO tool, which validates the data and the assumption based on our initial configuration of those devices. Now we will move forward describing different activities that we have done through this year. The first target was to upstream the Virtio-loopback driver into the kernel community. To do so, we prepared a new pull request and we shared it with the Virtio dev and virtualization community with the objective to interact as much as possible, received comments and eventually merge this code to the kernel code base. To summarize this effort, as we said, we created the RFC, then we have the discussion detailing the architectural components and mechanisms, and at last we headed the discussion in security optimization that can be done to the technology. More specifically, we start working on development branch on Gerrit, investigating a new memory sharing mechanism based on a bouncing buffer technique for specific pages where the buffer is smaller than the page, in order to avoid sharing kernel data with the user space, with a trade-off of the performance. The links below can route you to the RFC discussion in the kernel and in the development branch that have been done for the bouncing buffer. Other activities were related to meta-eg layer, more specifically fixing CAN driver for Raspberry Pi and the AGL reference hardware. Then we focused on the VIOS user applications and mostly on the sound, then on CAN, console and input. They're all available now and you can use them from your virtualization environment on or with Virtio-loopback. And at last we created a new dynamic layer for Raspberry Pi and the reference hardware for the Virtio CAN and CAN drivers to be included into the build. During this year we were able finally to merge the VIOS user development that happened during those 2 years into the Rust VMM community. Now this device can be used for both loopback and KEMO. Next, upon a request that we have done, the community created the CAN console and input crates.io binaries, which we are utilizing from the Yoros or Yocto recipes those days. During the development of the multi-device and prioritization feature, we had the opportunity to work more on the adapter and make it more device agnostic, but also the whole architecture. This means that we have separated the process of adding new devices and the files that are mainly focused on the logic of the architecture. So adding a new device is a much easier process, but also upgrading the whole logic and maintain the whole project has become a much easier job. Now let's start finalizing our conversation by focusing in the next steps and the future developments. As we have seen today, Virtio-loopback starts becoming a fairly mature technology which supports many Virtio devices. Ongoing discussions are more focused for future developments or implementing demos that showcase its impact and mostly on container workloads and extending its list of Virtio devices and use cases. In this and in the next slide, we start discussing how Virtio-loopback can coexist with container and VM workloads and make them work collaboratively. So this demo specifically is utilizing the Zephyr OS for reading from accessing real hardware and reading real CAN messages, and then after filtering them, distribute them to the IC and IVI containers via the Virtio-loopback architecture. What is interesting in this demo is that various user devices in user space can work not only for accessing real hardware but also for as a shared communication channel. The next scenario presents a bit more different and abstract idea of utilizing Zen together with Virtio-loopback. More specifically, it extends the ability of Virtio-loopback and tried by using it to standardize inter-domain communication between Virtio and various user devices. That gave us the ability to use the very same driver as before as communication channels, but at the same time have a very strong compartmentalization for automotive applications. At last, adding support for more devices into the architecture such as I2C and SCSI will bring it much closer to embedded systems, and support for frameworks such as DPDK, SPDK will bring the technology more relevant to cloud scenarios. Thanks a lot for watching. Please feel free to contact us and share any questions. Thank you a lot.